Hi everyone and welcome to the next exercise, this time on break-in moment optimization, where you already have assigned patients to rooms and maybe days, but not the actual schedule. So your task is now to schedule 5 patients to operating room 1 and 2 with given the duration of the surgeries. Okay, so we know that the operating room is available from 8 a.m. and the question is, in which order and sequence should these patients be assigned so that we be as close to these break-in intervals as possible. Okay, so that we have enough break-in points and moments where we can assign emergency patients if necessary. Okay, so let's start with the first task. Calculate the latest start, the earliest end date and the lower bound lambda. Okay, so we know the durations. We know that we have 5 patients and they already have been assigned to operating room 1 and 2. Okay, so obviously the starting point is the same for everyone at 8 a.m. Okay, and then the question is the earliest end date or end time, let's say it like this. In operating room 1 we have, if we start at 8 a.m. plus the first patient requires a duration of 1 hour, the second 1.5 hours, and the third one 2 hours. That means we will finish these patients at 12:30 p.m. Okay, so this is operating room 1, and in operating room 2 we start again at 8. Wait, just let me make the 8 here clearer, plus half an hour for the 4th patient, plus 3.5 hours for the 5th patient. So we finish in operating room 2 at 12 p.m. Okay, so that means it follows that our earliest finishing time is at 12 p.m. Okay, so that means our occupation interval, so where all operating rooms are occupied, is between the latest starting point and the earliest ending point, and this is in our case from 8 till 12. So meaning that it has a length of 4 hours. Sorry. So a length of 4 hours. Okay, so between 8 and 12 all operating rooms are occupied, and now we have to check where the break-in points are so that we can assign emergency patients if necessary. For this we would like to determine the lower bound. Okay, so the formula was, as you might remember, as the occupied interval E minus S, and then 1 plus, so this is the first interval, plus the number of surgeries plus the number of operating rooms. So in our case it's 12 minus 8, and then we have here 5 patients for two operating rooms, and that means we have 4 divided by 4, and our lambda would be 1 hour. Okay, so that means we should assign the patient in such a way that every 1 hour one surgery ends and we can fill in an emergency patient. So we have break-in moments every 1 hour. Okay, so this was the first task we had to answer. Let's start with the second one. So use the fixed goal heuristic to sequence these surgeries so that we are as close as possible to this lower bound. Okay, so we went through this heuristic in the lecture, so let's apply that. Here we start with the first task is to determine for each unscheduled surgery the completion time if it's scheduled next. So the completion times are 1 hour, 1.5 hour, 2 hours, 0.5 and 3.5. Okay, so because none of them have been assigned yet, therefore for each patient these are the completion times. Okay, next is to determine the for each operating room to determine the maximal completion time. So obviously that would be 2 here and 3.5 here. So it's also written down. Okay. And then determine the set of surgeries such that their completion times is less or equal than the minimum of the maximal completion times computed in the previous step. So first of all, we have to say that this is the minimal maximal completion time. Okay, so that would be in our case 2. This is the minimum of our maximal completion times for operating room 1 and operating room 2. Okay, and that means which of these surgeries or the patients can be assigned. So obviously the first one is possible because the current duration is only 1 hour. 2 is also possible with 1.5 hours of duration. 3 is possible too, so exactly on time. The 4th patient is also fine, but we cannot schedule the 5th patient because its duration exceeds the minimum of the maximal completion time. Okay, so therefore you can see here that we can assign patient 1, 2, 3 and 4. Okay, so whom to assign now? The last point is from that set determine a surgery such that the difference, this one is minimized. Okay, so we had the surgery for patients 1, 2, 3 and 4. Okay, so we know that lambda is 1 hour. We are currently in the first iteration step, T is 1. Completion time depends on the patient, and capital S we start at the beginning of the planning horizon, so it's simply 0. Okay, so it's 8 o'clock, so we start with 0. Okay, so if we look which patients would minimize that, then obviously you can see here that surgery 1 would be chosen, or patient 1 would be chosen, because that would mean 1 times 1 minus completion time of patient 1 is 1 minus 0 of capital S, and that would give us a 0 here. Okay, so it cannot be less than that. This is why we will choose surgery 1 and patient 1 to assign first. Okay, so that means here this patient has to be assigned, okay, to the first operating room as the first one. Okay, and the next step would be to check if we have unscheduled patients. Yes, we do have. That means we now have to set the iteration number to the next one and go back to the second step. So what does it mean? You can see here the first patient has been assigned, and then you can see the iteration was set to 2, and here the second patient, the completion time is 1.5 plus 1, and we end up with 2.5 hours, and the same 1 plus 2 hours, and we end up with a completion time of 3. For operating room 2, nothing has changed. Okay, and the same again, what we can now say is to check what is the maximum completion time. So obviously for operating room is 3. For the second operating room, it's 3.5. So that means we're choosing this one. And this is why we are writing that in the minimal maximum completion time column. And then again, we are having to say whom to assign to which room. So in this case, we could choose between the second patient, the third patient is also fine, the fourth patient also fine, but we cannot assign the fifth patient because the completion time would exceed our minimal maximum completion time of 3. Okay, so that means potential patients or surgeries then 2, 3, and 4. Okay, and again, we would like to minimize the deviation from this lower bound. We know this is lambda times t minus completion time of the respective patient, minus s. Okay, and we need the absolute values for here. So if we choose patient or surgery 2, then that would mean we have lambda of 1 hour, we have the second iteration, minus the completion time would be 2.5, okay, minus capital S, which is 0 all the time, and then we end up with minus 0.5, and because we have absolute values, so we have a deviation of half. Patient number 3, the same basically, so it's 2 minus the completion time is 3, okay, we have minus 1 here, so we have a deviation from 1, and then the fourth patient, 2 minus, and the completion is 1.5, and here we have a deviation from the lower bound of 1.5, and this is why we are choosing the minimum. So the next patient we assign to operating room 1 is then patient or surgery 2. Okay, so this here is nicely written again. Okay, so we have chosen then the second one. Okay, and the same again, so that means the second one is completed, and therefore we have a completion time. So the iteration is set up to 3. Okay, and the completion time, so we have assigned patient 1 with 1 hour, patient 2 with 2.5 hours, and then the next one would be patient 3 with 2 hours, and therefore the completion time is here 4.5. For operating room 2, nothing has changed, it's still the same. We have again checking the maximum completion time, which is 4.5 for operating room 1 and 3.5 for operating room 2. This is why we are choosing the minimum one and also placing it here then. And then the same again, whom to assign. So we can assign patient 4 and 5. Okay, so these are the potential ones. And here we can see again, so lambda times 1 times t is 1 because of lambda 1, and iteration in number is currently 3. So 3 minus either 0.5 for surgery 4 or patient 4, and 3 minus 3.5 for surgery and patient 5. Okay, and of course we take again the minimum deviation, so we would schedule the surgery 5 next. Okay, and then at the last one is obviously, let me go to this one. Okay, so this is the last step basically. We have again the maximum completion time 4.5 and 4, but we can only assign patient 4 because the third patient would exceed this minimal maximum completion time of 4. This is why we can only schedule patient 4 next. Okay, so at the end we have this schedule. So in operating room 1 we have the order, the third patient first and the second and the third, and in operating 2 we have the fifth patient should be assigned first and then the fourth patient. So this is the result. Okay, and now the question is, we have to determine the largest break-in interval and compare it with the lower bound lambda, which is 1 hour. And the question is the resulting schedule really the optimal solution? Okay, considering of course that we would like to minimize the maximum break-in interval. So let's have a look how it goes. So we have this, right? We have the schedule. We have operating room 1 here and operating room 2 here. So we know that we would like to assign 1, 2, and 3 patients in this order, and in the second room 5 first and then 4. So we start both operations in operating room 1 and 2 at 8. Okay, so the first one ends after 1 hour at 9. So this is the first break-in moment after 1 hour. Then the next patient starts, the second one. It takes 1.5 hours. Okay, so that would be the second break-in moment. Then in between, the fifth, which requires 3.5 hours, ends at 11:30. Okay, so that would be the next break-in moment after 1 hour. And the fourth patient just need a half an hour operation. Okay, so they will finish at 12 p.m. Okay, so that would be the next one. So these are the break-in intervals: 1, 1.5, 1.5 an hour. And you can see here that twice we could hit exactly our lower bound. One is lower than that, and only once it is larger than 1 hour. And it is still optimal, because even if you can see that the solution, we have 1.5 break. So in the worst case, if an emergency arrives at 9:05, then they will wait for 1.5 hours. Okay, but the problem is that the duration of the fifth patient requires 3.5 hours. So even if our theoretical optimal lower bound would be 1, we cannot hit it all the time, because the longest duration time is 3.5 hours. Okay, even if we would like, we cannot simply. It's not possible to reach exactly 1 hour every time. Okay, and the last task is there a more, or is it in general, are there more optimal solutions? And if so, then which one would you prefer, according to which criteria, and if yes, why? So I've wrote here simple one possible another schedule, that we switch simply 4 and 5. Okay, so that we start with the fourth patient first and with the fifth at the end, and we leave the operating room 1 order as it was. And you can see here then that if we change that, so we start with the fourth, we have after one surgery, after half an hour, the first break-in moment, then after another half an hour, another one, then the second patient is requires 1.5 hours, so from 9 till 10:30, and then the fifth is done again after 1.5. Okay, so that means if we talk about which to prefer, then obviously we would still prefer our previous solution, because here we have 2 times 1.5 break-in intervals, so twice we don't reach our optimal lower bound of lambda of 1 hour, although we have twice half an hour. So that means if the emergency patient arrives in a not really good time at 9:05, then they would need to wait 1.5 hours, or if they arrive at 10:30, 35, then another 1.5 hours. So this is why we rather prefer to have more break in intervals that are close to our lambda, so every 1 hour, instead of having half an hour twice, but then waiting 1.5 also twice. Okay, and this is why we still would prefer to have the previous heuristically found solution. And with this, I would like to thank you for your attention. See you.